UMTYMPers, welcome to video for section 12.8, more partial fractions. What I really want to know is, which one of you keeps putting thumbs down on these videos of mine? Really, who is it? Will someone admit it or not? Anyway, here's the problem. Partial fractions, find A and B such that, right there in the picture. I'm not going to read it. It's right there. Pause the video, find A and B. Welcome back. It didn't work. Or what I mean, I made you try that problem and I knew it wasn't going to work ahead of time. That was really terrible, wasn't it? I'm such a jerk. Okay, what happened? What happened? What happened was you had an irreducible polynomial in your denominator there. What's an irreducible polynomial? Polynomial is irreducible if the equation f equals 0 has no real roots. What does that mean, really? If f is irreducible quadratic, then it can't be written as a product of linear factors with real coefficients. If it's irreducible, that just means you can't factor it, right? You can't factor it over the reals. Anyway, you can definitely factor it over the complex numbers because we know that from fundamental theorem algebra. So this theorem here, we're going to prove it. We're going to prove it using the contrapositive. So the contrapositive says if f is a polynomial with real coefficients and it can be written as a product of linear factors with real coefficients, then f is not irreducible. So as a quick side note, what's a contrapositive? So if you have a theorem that says if p, then q, your contrapositive says not q, then not p. The contrapositive is logically equivalent to the conditional statement. So if you prove the contrapositive, you prove the other one too. So suppose f can be written as a product of linear factors with real coefficients. Then there it is. F is a product of linear factors with real coefficients. Then by the factor theorem, we know it's got two roots and that those two roots are real. So we can conclude that f is not irreducible because it's got two real roots. Proof complete. All right, give me some examples of irreducible polynomials. I already gave you one, x squared plus 1. That's irreducible over the real numbers. In the comments to this video, give me an example of an irreducible polynomial that nobody else has done that example in the previous comments. New theorem. If f is a polynomial with real coefficients, that polynomial f can be factored over the real numbers into a product of linear and or irreducible quadratics. So I can't always factor every polynomial into linear factors with real coefficients, but I can always factor it into linear or quadratic factors with real coefficients. The proof of this theorem is basically the fundamental theorem of algebra. There's a detailed proof in your book. It's on page 963. You should read it. It's super interesting, but I'm not going to go through it in this video. Who cares about irreducible polynomials? Okay, back to partial fractions. I got some rational expression here. I got a polynomial on bottom. If that polynomial on bottom has a linear factor ax plus b, and the multiplicity of that linear factor is n, the partial fraction decomposition has these terms here. Notice that the numerators are all constants and the denominators are all those linear factors, except you have 1 to the power of 1, power of 2, power of 3, all the way up to the power of n, whatever multiplicity that linear factor has. Okay. Here's a problem. Write down the partial fraction decomposition of this guy. You don't need to find the constants. Just write down what the fractions are going to be. You don't need to go through the whole finding what number goes in the numerator there. Pause the video and do it. Welcome back. So first step, I factor the denominator. Factor the denominator some more. And then each linear factor there has multiplicity of 1. So I know I'm going to have a fraction with each linear factor in the denominator. And then the numerator is going to be some constant. Try it again. Here's another one. Go for it. Pause the video. Write down the partial fraction decomposition. Welcome back. Here we are. So factor the denominator, x minus 3 squared. I have one linear factor. It's x minus 3. It has multiplicity 2. So I'm going to have two fractions here in my partial fraction decomposition. And I'm going to have a constant on top in each one. And I'm going to have one that has x minus 3. And the next one is going to have x minus 3 squared. Because the multiplicity of that linear factor is 2. Multiply through by the denominator on the left-hand side. Do a bunch of math. Get a equals 5 and b equals 14. All right, but what about irreducible quadratics? So, if the denominator has an irreducible quadratic of multiplicity n as a factor, then the partial decomposition has these terms. So what's different here? What's different here is the numerator is linear. If your bottom is an irreducible quadratic, the top has to be linear. So you're going to have two unknowns there in the top. And then depending on the multiplicity of your quadratic, that's how many fractions you're going to have, up to multiplicity n. Try this guy on for size. I bet you probably that there's an irreducible quadratic as a factor in that denominator. I don't know, maybe. Pause the video, write down the partial fraction decomposition. Hello, welcome back. Here's what I did. Factored the bottom. X squared plus 4 is an irreducible quadratic. So there's my partial fraction decomposition. My irreducible quadratic only has multiplicity 1. My two linear factors have multiplicity 1. The linear factors get a numerator of just a constant term, and the irreducible quadratic gets a linear numerator. Then you do a bunch of math. The method is exactly the same. You're going to multiply through by the denominator, equate coefficients, or choose convenient values of x, and solve for a, b, c, and d. That's the answer. Those are the values I got for a, b, c, and d. And I think, nope, we got one more. A word of caution when you're doing partial fraction decompositions. If your numerator has bigger degree than your denominator, don't try to do partial fraction decomposition right away. It's not going to work. Or if it works, it's going to be really hard and annoying. So don't do that. What you should do first, if your numerator is higher degree than your denominator, you're going to do the long division, and then you'll do partial fractions on your remainder. Yeah? Last one. Here is a rational expression. Find its partial fraction decomposition. And I will see you next week. I think we're doing an induction next week. That'll be fun. Bye, guys.